Now, just a reminder, this is just one episode in 4 in our series on CryoEM. Stay tuned for the other shows, or check them out. Check out the show notes here for links to them. Yusuke Yamada is an assistant professor there and an X-ray crystallographer. His colleague Toshio Moria is an associate professor and a CryoEM guy. And thankfully, I had Brian Shervin with me. He's our CryoEM guru on the HPC specialist team here in AWS, and he acted as my Sherpa through the whole experience. There's too much here, though, for one episode, so we're breaking this discussion up into 4 shows. In this final episode, we deep dive into the arsenal of benchmark data the KEK team have amassed, which the CryoEM junkies watching this channel can use to make your own decisions about what's going to be the best CPU and GPU combinations for you to use for your workloads at the resolutions you're working at. It's a long episode, but so rich with information, we didn't want to edit it down at all. Hope you get a lot out of it.
Users. So this is what we are aiming for, using cloud computer as a hub of the CryoEM of IoT. Then we can make the usage of the CryoEM much better. And on top of it, we can accumulate all our expense and knowledge and data on the cloud system.
And now I guess we're going to talk about a bunch of benchmark cases now. Mm-hmm. Brian, this is where I'm going to need you to help us interpret this, but I mean the benchmark cases are important, and this is one of the things that has also set KEK aside, because they've amassed a massive arsenal of benchmark data that's going to help people understand what kind of resources they need to apply to different scenarios, right? Is that the best way to interpret this?
Yeah, I think so. It's also the other real benefit here is, and I say this, so I did a bunch of CryoSpark benchmarking like a year and a half ago that kicked off a lot of the CryoEM stuff on AWS. But one of the issues with it was a pretty small set of benchmark data. That was useful because I needed to iterate a bunch, do a bunch of tests. I'm not a CryoEM scientist by trade, so it was also important to kind of have a pre-scripted run that I could do. But what the feedback we've got is it needs to be a larger, more real-world data set, and that's what the guys at KEK have done is this is actual real-world stuff that's of use. And beyond that, also they've done it on Relion. So when I did this, I just did it for CryoSpark. We've had interest in Relion, so it's important to have benchmarks for both applications. And they've also just done a lot of cost modeling, similar to what I did before, but. I did this before some of our newer instance types came out, like the G5 instances, for example, which is, I'm going to assume we're going to see is probably a better price performance metric. But so they've basically sort of, really expanded upon what customers are asking for in terms of benchmark data.
Okay, so this is one of our analysis result, and this is relatively small protein. It's called native nitrite reductase, and this is actual data. And we can reach to the with this data set, we can reach to under 3 angstrom, which is basically practical enough to be able to be useful for the drug design. So let's go. So we did actually try to use the real data set so that we know that what we can expect from the real data set. So that's why we choose this one. Okay, got it. So we choose that the 4 process steps, which is refine 3D, class 3D, and class 2D, and also polishing, because these are most time-consuming process and the most heavily used.
Yeah. Yeah. So I'll say one thing just to set the stage a little bit. So one thing that's unique about Relion is, as you've shown here, you can run this in both a CPU or a GPU mode. It will also run across multiple nodes. This is one thing CryoSpark doesn't do. CryoSpark will parallelize, it's GPU only. It will parallelize across GPUs, but only on a single node. And so this is just why we're seeing like CPU and GPU in larger numbers.
Yeah. So that this is something that we want to check, as Brian mentioned. So the Relion is flexible enough, so we can use the CPU version, means that using the tons of the CPU and try to make it faster, run faster, right? But also it's already also supporting the GPU implementation, so we can run the process with GPU. And also, on top of it, Relion is basically supporting the MPI interface, means that we can use many machines for one process. So massive power processing. And that's why that I did many different configurations. So this is the benchmark, and here that the left top is showing that the parameters which are related to the benchmark test, means that there's a processing time often, right? And so you can kind of tell that how heavy that this process can be. Okay, the left bottom is the result of the benchmark. X-axis number of cores or GPUs, so the machine power, right? So, and the Y-axis is processing time. And this is normal that the people put up for the benchmark test. And so, as you can see, that the left side is mainly CPU only, and we use the optimum version. So we use the Intel installer and use the CPU flag to run Relion with the optimized for the CPU, right? Intel chips. And then we change the number of CPU, so it's related to number of nodes, 100, 200, 300, 400. So it scales, right? And it's good. But problem is that we don't know cost. Well, let's put that. So okay, so start from here. So here, the right bottom showing that this top kind of the dot, the color is same. Round means that it's a CPU only, and most of them are really high cost level, because this graph is showing the x-axis is the process time now, and the y-axis is the total cost, how much it took to run this process, right? So, and we found out CPU solution can be faster, but problem is cost is very expensive. It's about $80. No, right? $80. So we figured out it's too expensive. So we moved to on the GPU. Again, the left bottom side that we see that this GPU. So we wrote this graph based on number of the GPU card, not node, right? So start from one GPU up to 64, we can see some scalability, but scalability saturate around 16 to 32 means that if we double the number of GPU, the processing time won't improve anymore.
Yeah.
But up to 1 to 16, it's really nice scalability in my opinion. So actually, you can use about 16 GPU. Many people use 4 GPU machine, or if they are rich, they might use 8. But 16, no, right? It's very expensive. So AWS is really great. Okay, so we tested this annotation is showing what kind of type of the computer we use, the EC2 instance we use for the parallel processor. So G4DN was very, very cost effective and fast for us. So we decided using this. And then this vCPU 48 means the 84 vCPU this machine contains, and GPU 4 GPU card, right? So one is just GPU one. So we use a different machine type, but basically use the same number of the GPUs as much as possible and did it. So using a different number of the different EC2 instance, which has a different number of the GPU, doesn't have any impact, right? It's almost flat. So that means that the number of GPU matters, basically. No.
So just to kind of summarize some of what you're saying, I think one thing that's really interesting is the cost modeling, because a lot of times we hear customers that think, they think of GPUs and they think high cost, and what you're really highlighting here is time to solution is an important factor in here. So you may be
the solution is a cost, right?
Yeah, and not only just like what is your time worth, but also in this case paying for the GPU instances are going to cost more than the CPU instances, but if you're running on them for less time, at least in this benchmark here, you're showing your cost is actually quite a bit less than some of the CPU instances, just because of how long it takes. Right. And then also the scaling part is really interesting. This is fairly similar to what we've seen with other CryoEM applications. Is massive. This is not a massive exascale type application. Running beyond about 8 or 16 GPUs isn't getting you much in terms of performance, and it's increasing your costs. So that kind of seems to be the takeaway from this benchmark.
Right. So thank you very much. So this GPU version is here. This is a zoom up view of the GPU machines, and as you can see, that this, as again, color code, same color means same type of EC2. And the only difference is that the number of nodes, 1, 2, 4, 8, right? So as you can see that if you increase the nodes, means the number of the GPU, it gets faster, but suddenly around 32, this is 32 GPU.
It's definitely plateauing, isn't it?
Yeah, it goes up, means that its scalability almost null, means that you're just basically wasting your money. This is a class 2D result, right? So again, that we can see the CPU version, going up. Scalability is okay, and but it's very expensive. Around here, the right bottom showing that the CPU version is expensive, so it's same trend. The only difference is that this class 2D scales really well with number of the GPU. So it scales up to 64 and maybe more beyond if we can use more GPU, but we couldn't use it because of limitation of the number of the vGPU that we can use. So there is restriction. We didn't apply more.
Just account limits were getting in the way at the time, right?
This highlights something that I think is really important to bring up in these CryoEM workloads. Is each of these stages is almost like a mini app. Each stage in this pipeline is almost like a mini application unto itself that you need to benchmark, and there are going to be different instance types that perform better or scale better. And so it's really important, and I'm going to tout AWS here, it's really important to have that kind of flexibility in the compute resources where you can run on an 8 GPU node one time, on a single GPU node on one time, possibly on a CPU node the next. And I think you're seeing that with these different scaling metrics.
And Brian, is this just a case where we have a chain of like dependent jobs in Slurm, each of them running on a different kind of infrastructure, potentially in different partitions?
Yeah. Each of these stages is going to run on its own, and it's one thing we didn't really cover. Both CryoSpark and Relion are aware of job schedulers like Slurm, and this is some of what folks at KEK have done is eliminate the need for the users to have to configure that or even understand what Slurm is. They can literally interact with the Slurm scheduler through the application.
Oh, wow.
And just know that, I need to run this for this stage because of the benchmarking that people have done. I know I need to do 2D classification on at least 8 GPUs. I can just select that queue from Relion. I don't even have to know that it's a G4DN or anything.
This is cool. Cool. This is making scientists really productive. I love it.
Thank you. And also the cost is, as you can see, that this blue line is almost flat, right? And this is the brown, and this is the greenish one. The only difference between the circle and the square is either spot instance or non-spot instance, right? On-demand instance.
Oh, all right.
So but the cost effectively is very clear from this one too. So it's flat. Means that even though you use the more CPU, the total cost doesn't change. So for the class 3D, I'm recommending use as many as GPU as possible, that if it's available.
Right. Good solution. Okay.
So class 3D, it's between it's more like refined 3D. So there is a linearity. So just I'm talking about GPU, right? So it goes down up to 32 and maybe 64 a little bit. But there seems to be saturation around here. So the class 3D and the class 2D has a really higher scalability relative to the GPU, but defined 3D has a earlier saturation in terms of number of the GPU. So you have to think about how to balance the configuration of the parallel processing depend on each process. And also we did polishing because one of our users strongly asked please do the polishing because it's one of the slowest processing in Relion. But to reach to the really high resolution, we had to run it, right? It uses a movie, which is the original input image data, but it's a really huge, like terabyte data set. And also this one is heavy, but it's not supporting a GPU. So we had to run CPU version. And so we did use many different CPU instances, especially C5, right? And no, actually, it says we only use the C5 instances because we wanted to use the Intel version of the Intel machine and also the Intel compiler, right? So we did it, and the scalability is not that great, but it goes down. But
so it looks like we've got pretty good scalability here, at least up to a point, up to around 192 cores, which that's probably only a couple of nodes, right?
Well, it's relatively flat, so that the somehow spot instance giving me much better impression of the scalability and cost effectiveness because it's flat here, right? But the on demand is going up from the 2 node to 4 node very suddenly. So, and 8 even more. It's kind of difficult to figure out which is the best so far for me. I don't know, maybe that 192 seems to be okay, but more than that, maybe a little bit too expensive.
Well, it'll vary also a little bit on what structure they're looking at and different parameters and whatnot. But I think the important thing here is again getting some of these the overall behavior and like what how do these things scale? It's probably pretty clear that the polish one isn't going to scale massively. So start with something kind of in the middle and iterate from there in terms of other benchmarks. So
yeah, true. Okay. And also interestingly, that the per node MPI process will change at the beginning, right? When that I'm using one node, but when I started using multiple node, it will diminish. The difference will be diminished. So we don't know why, but it's kind of interesting. But I'm recommending the user to use to set that the largest MPI allowed for the memory so that it runs faster. Usually it can run faster. And so this is actually the new result. We mainly wanted to check the G5 instance. So the top part is G5. So the left side is G5. And from this the blue kind of color, it will be G4DN, the previous one that we used. So difference is clear. G5 is better in terms of speed if the number of the GPU is same. So if you want to just think about the GPU, number of GPU, just use the G5. Interestingly, cost one here is saying that basically the speed might not speed might be faster, but also the cost is expensive. So for example, so I'll be using this dot yellow one, right? This is a 2 node of G5, and this yellow one here is 4 node of the G4DN. And the processing time is almost same, and it's a little bit difficult. So the 4 node and this 4 node is better. So the cost goes up if the number of the GPU is same, or the number of GPU is same. So that means one GPU is twice faster, but the G5, the cost of G5 is almost twice expensive. So as a result, cost effectiveness is not so clear. But the point is that you can actually, if you are using G5, then it's much easier to make your process goes faster because you can use more machines.
Right. So this is just a case where, I mean, I think this is, we see this a lot in HPC, more or less whenever we see new generations of CPU architectures come along, right? Newer is usually better. That's usually a good rule of thumb, or at least it's a good starting point for an analysis. What you're saying is newer is definitely better. Newer is also often more expensive, and that's pretty common too with most, with most new processors, new GPUs especially. And you're saying those two things balance each other out, which is interesting because it's not, I mean, it would be much better if newer was faster and cheaper. That'd be the holy grail. But in this case, they balance each other out to the point where you can choose, I guess you choose based on availability. Older may be more available than newer. That's possible. And of course, the other balancing act is just the speed at which you need to execute your analysis. You can actually choose how fast you want to get it done. Yeah. Okay. Understood.
So this is the one of what Brian was talking about. So I wanted to really try the real case scenario, which is we wanted to go under 2 angstrom resolution, right? So I pick up this Empire dataset, one of my friends did, and actually it's supposed to reach to the 1.93 under 2 angstrom resolution. So this was a really great example. And also it's a very small protein, so it's not easy. So this is the result. So what I wanted to do was that I wanted to check whether how much to reach to the certain resolution, how much it will cost, because we know higher the resolution, more expensive, right? So I did process, and around job 140, 100 jobs that I reached to the 2.23 angstrom, And this is okay because we can see the shape of the aromatic ring very clearly, but still we can't see the hole. Maybe small, if it's lucky, we are lucky, we can see hole of the aromatic ring, right? Especially 6-member ring, right? And it costs about 1,142 hours. Then I continue the process, and then when I reach to the 1.95 angstrom, it costs it twice as much as previous. So basically, try to increase about 0.3 angstrom, I guess. That it costs twice means 1,000 again. And also the hours, the time doubled. Okay, I'll skip this one because it's almost same. So the last one that I reached, the best the resolution I reached was 1.83 angstrom, which is pretty nice and actually higher than the published data. So I was very happy. And then it costs again twice. It's now $4,800, right? And also the time is double too. So this is something, the resolution that you have to think about, you have to think about balance between cost and resolution. What resolution you really want to have? Because it's easy to say highest resolution, but do you want to pay for it? How much you want to pay for it, right? So also this is very important for us because to promise our customer, okay, we can do the processing within a day with this amount of money, we have to limit resolution to promise. So this was very necessary, basically analysis for us to basically tell what we should tell to our users and what we should promise, right? So this is what we did. So
to say a pharmaceutical company, what's the value of being able to get that kind of resolution? Is there a way that they can translate this into part of the downstream process of designing a drug when they go to do things like docking and whatnot? Is this time and money well spent, or is it simply like chasing a number for the sake of being able to say I've got the lowest resolution structure ever published?
It depends, right?
It depends. Yeah, it's very difficult to say.
Okay. I have learned so much about CryoEM in the last few minutes. So this has been eye-opening to me. It's been also really interesting to understand, what the solution that you guys have come up with that works across all of Japan. You've concentrated a whole lot of expertise into the software stacks you've built and the methods you've done so that all of Japan can take advantage of this. I think there's probably a few continents and countries that could take a lead from this and do something similar. But as is oh so frequent, when it comes to the use and the application of HPC to real problems, Japan is way out there in front of us, in front of the rest of the world very frequently. So I guess with that, Moriya-san, Yamada-san, thank you for coming and joining us and explaining that to us.
Well, thank you very much too for giving us this opportunity. It was really great.
Now, just a reminder, this is just one episode in 4 in our series on CryoEM. Stay tuned for the other shows or check them out. Check out the show notes here for links to them. If there's something you want to see us cover in a future episode of Tech Shorts, come and find us on Twitter. Our DMs are open. Arigatou gozaimasu.
こちらこそどうもありがとうございました。
Thank you.
Thanks.